In this video, we will talk on more on the terms related with radiation. So this topic is about radiative properties. So you need to know what is opaque, transparent, and semi-transparent. So here there's an image. So for opaque, you cannot see the underneath wording below the cloth. Okay. For this one, it's semi-transparent, and transparent you can clearly see through the underneath writing underneath the cloth. So that is the difference between opaque, semi-transparent, and transparent surface. Okay, so for many material that we encounter in practice, such as metals, wood, bricks, they are opaque to thermal radiation, and radiation is considered to be the surface phenomenon, so it won't absorb to the underneath material below. Okay, so in this material, the thermal radiation is emitted or absorbed within the first few seconds of the surface. Okay, just for opaque, we just deal with the surface. But some other materials like glass and water, they exhibit different behavior at different wavelength. So sometimes they can be just opaque, and sometimes just they could also be a semi-transparent depending on the wavelength. So here we have visible spectrum and infrared spectrum. Okay, so in this video, this short video is all about the theory part. We will not deal with any calculation. You just need to get yourself familiarized with the terms. Okay, so next is emissivity. So you must be very familiar with this because we have deal with this in chapter 1. So emissivity is E, small e, epsilon. So it is a ratio of radiation emitted by the surface at given temperature to the radiation emitted by a black body at the same temperature. Okay. So it is a ratio, so it is unitless, and the value is between 0 to 1. So 1 is for a black body. And for the emissivity of real surface, so other than black body, it varies with temperature of the surface, wavelength, and also the direction of emitted radiation. Okay, these are the three factors that affect the emissivity of real surface. Next, you need to also know about the spectral directional emissivity, where it is the most elemental emissivity of a surface at a given temperature. So, most elemental emissivity. Okay. The most elemental is referred to the spectral directional emissivity. Okay, next is about gray and diffuse surface. Okay, for diffuse surface, it is a surface which properties are independent of direction. So if you look here, if you have semiconductor and conductor, the axis is emissivity versus angle of the radiation. So they are independent of the direction of the radiation. And unlike for gray surface, it is a surface properties that are independent of wavelength. Okay, the graph is emissivity versus wavelength. Okay. Okay, these are some other example. Okay, for gray surface. Okay, next is about absorptivity, reflectivity, and transmittivity. Okay, when a radiation, so the red arrow here is a radiation. Okay, part of it will be reflected, and the green arrow and the blue arrow here, some of it will be absorbed by the surface or transmitted, okay, transmitted through the surface. So your incident radiation is equal to transmitted plus absorbed plus refracted. Okay, your absorptivity is defined by a term alpha. Is your absorbed radiation versus divided by incident radiation. Okay, reflectivity is rho, reflected radiation, Graph, divided by incident radiation. And the last one, transmittivity, TARC, is the transmitted radiation divided by incident radiation. So here, just like I said, your total G is equal to all the radiation from absorbed, radiation reflected, and radiation transmitted. Okay. The first law of thermodynamics requires that the sum of absorbed, reflected, and transmitted radiation to be equal to the incident radiation. So if we divide all this term with G, so you get alpha plus rho plus TARC, which is equal to 1. For opaque surface, okay, you will not have a G. You will not get to this side. So you won't have TARC. So your TARC will be equal to 0. So alpha plus rho equals to 1. Okay, and this definition are for total hemispherical properties. Okay, these are just the derivation. You don't need to know at this stage. Okay, what's important here is the last concept here, Kirchhoff law. So Kirchhoff law is related when you have let's say you have a small body of a surface area A, emissivity E epsilon, and absorptivity A at temperature T contained in a large isothermal enclosure at the same temperature. So if you recall back in previous video, large isothermal enclosure forms a black body cavity regardless of the radiative properties of the enclosure surface. Okay, this is like one example of the black body, where for a large cavity with a small holes, okay, the body in the enclosure is too small to interfere with the black body nature of the cavity. So what important in Kirchhoff law is your epsilon, okay, emissivity is equal to absorptivity at the same temperature. So basically that is the concept of Kirchhoff law. Okay, you need to remember this. E equals to alpha. Okay, but there are strict conditions inherent to the derivation of the Kirchhoff law. So these are the 3 restrictive conditions. So the first irradiation corresponds to the emission from a black body. So if it's not black body, you won't have a Kirchhoff law. Okay. The surface temperature is equal to the surface temperature of the source of irradiation. Okay, your temperature must be the same for E and alpha. Okay, for that 2 surface, and your you must be at the steady state. So these are the 3 restrictive conditions. Okay, the relation is valid when irradiation or emitted radiation is independent of direction. So at any direction is fine. Okay, and also involve no restriction to the spectral directional form. Any direction is okay, and any wavelength is still valid for both emissivity and absorptivity. Okay, as long as you follow these 3 restrictive conditions. So basically these are the terms that you need to know related with radiation. Okay, that's all. Thank you.